Hey everybody, welcome back. This is the long-promised lectures number 14 and 15 in a great huge ball, covering a lot of topics in analysis and inferential statistics. So before we get into the nitty-gritty and all the lovely math and stuff, we're going to just take one moment to raise a glass to a new president and to a great hope for the future being a lot less chaotic than the recent past. I feel ready to face the next 4 years. I hope you do too. So, let us get into it. All right, ladies and gentlemen, today we're going to be talking about prediction, modeling, and inference. I'm going to give us a bunch of shorter lectures to cover what is fundamentally 2 full hours worth of material. Okay? And today's learning objectives, we're going to talk about the different kinds of questions that are appropriate for inference, right? What kinds of questions do we use an inferential thing on? What kinds of questions is it not appropriate for? We want to understand, by looking at something, to identify whether it's a good candidate for this approach, okay? We'll also want to look at modeling, creating models, understanding very formally what we think is happening in a set of data, what the causes are of something, is a special approach, a little different than the generic inferential one. And we want to understand what variables are necessary to do that, and also, again, when that approach is appropriate, when it's not. Okay. We also more generally want to talk about things that are going to happen when it's impossible to do inference right, okay? Where you think, oh, I've used some beautiful math, I clearly must have a valid answer, but oops, yeah, no, because you didn't check that a variable and it's not bell-shaped, that variable, so you can't apply that statistical technique to it, right? Those are the kinds of things that we want you to be able to identify. All right, so we have already been through this little graph a couple of times, right? Where do we start with any analysis? We always start at the level of descriptive analysis, right? When we have the data, if you don't at least look at it a little bit and see what's going on with it, you're doing yourself a disservice. If you try to jump right to some sort of statistical testing, you're going to miss things like I was just saying, where it turns out, oops, the variable you're looking at is not normal, it's not a bell-shaped curve, and so you can't do these various techniques on it, okay? So do your descriptive analysis first, each and every time. Now, sometimes you stop there at descriptive, like we've talked about, but often you'll go on to do something exploratory, especially if this is the first time you've worked with data of this sort. You will explore around, trying to see what kinds of things are there to see. Does it look like these variables are particularly important, or maybe they seem to just be random, right? Is there a relationship between A and B? So now we know that especially if you're doing something for the first time, that it may not necessarily hold true in a future analysis with brand new data, okay? The first time you see something, you could always be seeing random chance. You could always just be seeing a weird event where the dice rolled double ones, okay? It happens. So we do exploratory analysis, and when we do exploratory analysis, we're only looking for big ticket items that are very clear, and even then we know they might not hold true. Well, today we're going to focus on the next steps, okay? So now one approach is that after you've done some exploratory analysis, maybe you have reasons to think that one measurement is affecting another. that A is the reason B happens, okay? And if you have some sort of analysis where you think A causes B, then you are in the world of causal analysis, okay? Trying to determine those causes. Now, we're not going to speak a lot about causal analysis today. It's a topic for another day. But the next thing is if you're not trying to say A causes B, but you're just interested in trying to predict something, okay? We want to know what the weather's going to be like. Now, is it important for us that our predictions are based on exactly how the weather happens? No. All that's important to us is, can we accurately predict the weather? Maybe we use things as inputs to our predictions that are not directly related to causing the weather, but they're good indicators, right? Just for those of you who are familiar with the English phrase, red at night, sailors delight, red in the morning, sailors take warning, that, red sunsets indicate that you're going to have calm weather tomorrow, but red sunrises indicate you're in for some really big storm. Okay? So it's certainly not the color of the sunset or the sunrise that causes it, but something else causes both the change in the air, which makes the sunset or sunrise look more red colored, and that same thing is leading us to have a particular event, a storm, clearing out or coming into the area. All right, so predictive approaches are different than causal approaches. That's what I was just saying. All you care about is being able to predict. You don't care about the way the causality happens. So let's say we're taking a predictive approach. There's two broad classes that happen, okay? When you have a human come in and give you a bunch of data which has the right answers, okay, the correct answers to some problem, and we use that right answer data to train up our system, okay, then that is supervised machine learning. And oh my gosh, that I noticed just a second ago that those are not correct. I had to scratch them out here. The yes is on the right, going to supervised machine learning. A human labeled right answers to train the algorithm. Okay? So, and when the human does not produce right answers, but we just throw the data into an algorithm, and the algorithm looks at, these are more similar over here, and these other samples over here are more similar to each other, but they're not like the samples over there, the samples that are in the A group. I'm seeing two groups, group A and group B, based on similarity of measurements, okay? That would be a typical unsupervised machine learning approach. So supervised means we have labeled training data, data that we can use to get the right answers on new data that we've never seen before. Okay, that's a supervised machine learning approach. Okay, well, let's say we're not trying to predict measurements for individuals, right? So like a typical predictive thing is like, let's predict the weather tomorrow for a particular individual day, right? Or let's predict somebody's health status from a bunch of measurements we have of their blood levels for various kinds of chemicals, okay? That would be trying to predict individuals. Maybe we're not after individuals. Maybe we're after groups, right? Maybe what we're after is, from a set of health markers, what is different about people who are diabetic versus people who just have metabolic syndrome, which is kind of diabetes light, okay? What are difference between those two groups, okay? So in that case, we're not trying to predict individuals, we're trying to understand group differences. Oops. And that's when we're in the realm of good old-fashioned inferential statistics, okay? This is really what most people think of when you say statistics to them, right? They're oftentimes thinking of a hypothesis test of is group X the same as group Y. Okay. So I'm going to go through a bunch of subcategories of inferential analyses, okay? These subcategories, these categories of inferential analysis, they're not canonical. They're not the only categories that we can split out, okay? The reason why I'm going to talk about these categories is that they're very common data science sort of tasks, all right? And again, they're not the only kind of tasks that fall under inferential statistics, but they are common data science things, and they often have slightly specialized approaches compared to the normal kind of inferential statistics. We're going to talk more about them over the next couple of weeks for sure. So if data is about location, then we're in the realm of geospatial work. We're trying to understand the ways in which things move around or are distributed in space. And geospatial work has its own unique kinds of analyses. Now, if the observations are not spatially related, maybe they have to do with text. Maybe they have to do with a corpus of text. The word corpus just means a group of words or sentences or letters, right? So a corpus of text is a big group of text. And if you're working on text data, maybe you're trying to understand, is a particular book best categorized as a drama or a comedy or something like that, then you might be doing this kind of text analysis work. Now, finally, if you're not doing either of those, we're going to say that you're probably in this world that most people think of in statistics, where what you're looking at is these classical ways to test, is group A and group B actually the same group, okay? Based on these measurements, are they basically exactly the same thing? All right, so just to kind of summarize and give you another bite at all this, again, descriptive and exploratory data analysis are always the first steps, right? Of course, my thing's deciding not to work. All right, let's try again. There we go. Hey, I'm back. So you always start with descriptive statistics. If you don't start with descriptive statistics, you're not going to know that you have a bunch of missing data, right? You're not going to know that, hey, half of my data is missing. You're not going to know that somebody recorded their height in feet instead of in inches the way they were supposed to, just like all those things we've seen in lecture, okay? So you always do the descriptive work. And if you are coming into this analysis for the first time, you're going to probably do exploratory work as well. You're going to try to see what are the relationships that I can find in the data. Now, if you find some relationships that you want to go and look at in more detail, then you're going to go on to the inferential work. Or maybe you don't need to do exploratory data. Maybe there's been previous work that has happened in very similar data sets, which has told you that you want to go looking at the relationships between A and B, and you don't need to do any exploratory work at all. You can just go right to doing inferential statistics on A and B. Okay? So inference establishes relationships. The whole point of inference is that we're going to look at ways in which we can tell with surety that something is the same as something else, or that it's different. Now, sometimes we also do modeling with these kinds of things, where what we're trying to do is we're trying to fit a model which describes how, right? Not just that there is a difference between group A and group B, but the ways in which that difference arises, okay? So we can potentially do that as well. And I'm having some Wi-Fi problems. Yay. Okay. While I try to deal with the Wi-Fi problems, I'm just going to finish this out by hand. All right. Let me see if, did that show up? Yes. Okay, good. That appears to be working. I can do it by hand. All right. So geospatial analysis, text analysis, these are specialized things in the sense that we use particular techniques to address these kinds of inferences, okay? The whole idea of how inference works is still the same, but some of the individual techniques are unique to geospatial or unique to text analysis. I'm also going to mention time series analysis. I'm going to mention it because I know that a couple of groups are maybe interested in doing something like this. Stock market prices changing over time, right? COVID or other diseases changing over time. When you look at stuff that happens over time, you can apply particular analysis techniques that are specialized for that kind of work. Now you can also address them in the normal inferential classical statistics. You can just test, is group A different than group B? Are technology stocks different than manufacturing stocks? Is the stock market before 2001 different than the stock market after 2001? Okay, those are not time series based things. They're just the classical, is it A and B the same, which often classical statistics gets into. All right, so you can do the classical statistics work on time series stuff, but there are also special ways to look at things in fine detail over time. And I'm going to see if I can find a place to put some of this material in the course. We haven't been covering it in the past, but because there's some groups interested, I'll try to shoehorn some things in. And if I don't find a way to do that, we can still talk privately on your own work. All right. So now we also mentioned machine learning, right? Machine learning is usually used for mostly for prediction, mostly for the case where what we care about is the results of predicting for an individual sample. So to use my own work, right, we have a bunch of things related to gene expression in the body, right? The way your body's genes work is that they're there waiting around most of the time, and then sometimes your cell goes, oh, I need to make some of this gene. I need to turn this gene and turn it into proteins that my body's going to use. Okay, so that's called gene expression. How much of your genes, of a given gene in your body, is turned on in a given cell to make a given protein. And it turns out that you can use information about gene expression to look at all kinds of things. And one of them is aging, right? We're pretty sure that aging involves a lot of things, including genes turning on and off. We don't really know exactly what aging is. We don't know how aging works. But if we want to predict how old somebody is, we can use a bunch of measurements about gene expression, and we can make a pretty good guess, given gene expression, how old somebody is. Now, are the measurements we're using to predict somebody's age actually important for aging? Is it directly how aging is working? No, right? But we can predict in a sense that we have this black box and it gets reasonably good answers, all right? Relatively good at predicting somebody's age, but we know it's not actually modeling. It's not actually a model of how aging changes genes, right? It's not a good model of how the aging process works, but it is good at predicting how old somebody is. So I hope that helps you understand the distinction between prediction and modeling, right? On the one sense, the predictor just cares about the answer. We only want to know what the weather is going to be like tomorrow, okay? We don't need to know how it gets to be that way. So, the red at night, sailors delight. Red in the morning, sailors take warning, okay? We only care about the results. We don't care about if we have a good model of how that storm is going to arrive in this area. Right, so supervised and unsupervised machine learning are different ways in which we do this thing. I will also mention that there is in-betweeners, okay? There are things which are semi-supervised or self-supervised where the machine learning algorithms may take, say, a bunch of labeled data about what is a positive word and what is a negative feeling word, and then it may use that data for itself to be able to learn how to recognize other positive feeling words and negative feeling words. And then it will label things for itself after that point, okay? Or you may take a machine learning algorithm and train it with data that is good and also with a noisy version of that data where you purposefully noise it up, okay? And by training it on data which is good but not labeled and the noisy form of that same data, then we let it self-supervise itself. We let it learn how to recognize noisy things, okay, without us telling it this is an A, this is a B, this is a C, right? It just learns to autocomplete things, essentially. All right, so don't worry if you don't understand. These are topics for a more advanced machine learning course, all right? But the point is that I wanted you to understand that there are different forms of machine learning. So, causality, we also mentioned. Now, experiments are the best way to establish that there's a causal relationship, right? We do something like use a randomized controlled trial, okay? Randomized controlled trials are the best way to convince somebody that you understand that A causes B, all right? Let's say we have a bunch of people who have a certain disease, right? They have diabetics. And we're going to have a group of control diabetics who don't get a medicine. They just live their lives as they already are on insulin, right? And we have a group of treatment diabetics who are going to get this new medicine. And we use that randomized controlled trial structure. We follow both the control group for a while, and we follow the group that's getting the treatment for a while. And we compare the two groups. And because we see them at the beginning before they get treated, and then the group after it gets treatment, and the other group goes through that same time frame and gets no treatment at all, the control group gets no treatment, right? Then we can compare those two groups and their progress from the beginning of the experiment to the end. And that enables us to say that any kind of difference we see in the group with treatment is due to the treatment and not due to random chance. Okay, this is the gold standard to establish that the treatment is the cause of the change in the diabetic's condition. So another day we're going to talk a lot more about that kind of stuff. But today we're really much more focused on the inference. Okay? I also just want to mention that there are some other ways in which causality can be established. They're not just beyond the scope of this class. They're beyond the scope usually of your first 2 or 3 probability and statistics courses. But there are specialized inferential techniques that are made to try to understand causality. Another way in which people understand causality is through well-validated models. If we have a model that predicts how the weather is going to change, and it's really, really good at predicting how the weather changes, and it's never wrong, then maybe we have to consider the fact that what the model is doing is not actually just looking at things that are related to the weather changing and figuring out how to predict the weather, but it's actually looking at the real underlying causes of the changing weather. Okay? So a model which has been around a long time, which doesn't have any data which contradicts it, can be seen as evidence that the model itself is a good model of how the thing actually functions, the whys and the hows, not just the prediction end of things. All right? So let's look at a few examples so this stuff is much more clear for you. All right? So if we have that general question, what impacts politics in America, we can refine it, right? We know that's too generic of a question. We want to get at something that's addressable with data science, right? So we have to make clear what we're measuring and what the implications are of our investigation. So we refine our question down to the level of, is there a relationship between the sentiment of political words in the cartoon South Park and America's presidential approval rating? Okay? Are we saying there's a causal relationship here? Come on, somebody. I can wait up here all day until somebody answers. Yes, green hat. Yes, you're right. We are not saying there's a causal relationship here. Correct. What we are saying is that there's a relationship. We don't know. It could be that South Park's political phrases they use influence how we think of America's president. South Park is, so popular, or at least it used to be, that, it can affect how Americans think of their president. Or it could be the other way around, that as America's president becomes deeply unpopular, the writers of South Park react to that and change what they're doing. Those are two very different causal directions. We don't care. We don't care. We're asking a question which is asking, is there a relationship? We're not saying which one. Okay? So let's get some data. Let's look at number of times the word vote is mentioned during the South Park episodes. Okay? Or the number of times this censored word is mentioned, right? And we can use data like this to see and correlate and look at presidential approval rating at the same time as these episodes of the cartoon. All right, so this is, how does this look? Well, we're going to start with a descriptive exploration. So we're going to look at the data and see what it looks like. And then we're going to try to look through that data because there's a lot of words in South Park script, okay? We don't know what the right words are that might key on this question of sentiment. So we have to go exploring and look for the kinds of sentiment that are within South Park, come up with some sort of, say, groups of sentiments like positive or negative, or things that are like rebellious or follow the rules, can be another kind of sentiment, right? And we have to explore and find out what kinds of categories of things we're going to put into an inferential question, a question where we're going to actually ask, okay, now that we know that we're looking at categories of positive and negative emotion and categories of rebellion versus authoritarianism, and we've defined what those look like and what kinds of words fall in those categories, now we can ask the actual question, is there a relationship between these things that we're laying out and the president's approval rating, which is something we can download from the internet? Okay? So, and also I should mention, right, that there's these smaller things going on here, like, well, we need some particular analysis techniques for text and this classic statistics kind of question. All right. Another thing we might do is classification. We want to label stuff from a small number of possibilities. Okay? Can we predict which team is going to win the Super Bowl, or maybe the Champions League trophy. Maybe we want to predict the Masters tournament because we like golf. I didn't put that in there. Right? So there's a small number of competitors. Which one's going to win? Can we predict the genre of a movie from just its script, whether it's comedy or drama or whatever? Okay? These are interesting classification techniques. We want to just know from one of a small group what is going on. And this is fundamentally going to be a predictive task. Now again, we're always going to start off with a descriptive beginning and maybe an exploratory bit to try to figure out what the variables are that we want to use. Okay? But once we have some variables, then we're going to be doing this as a predictive kind of element. Who's going to win this year's tournament? Now, regression and classification are somewhat related, right? The difference is that classification says which one of a small number of things is going to be the case. And regression is trying to predict a continuous value, a number, a real number, right? We want to predict somebody's age, and age could be, right, like 43.897 years, right? It's not a small number, it's a real number, okay? Or we want to predict, how thick the sea ice is going to be, which is I'm going to get to in a second, okay? And that's a real number, and it can take on an infinite number of possibilities, not a small discrete set. So regression is for predicting real numbers, and classification is for predicting small numbers of counting numbers. All right. So examples are, can we predict how many COVID-19 cases a region will have next week based on Google searches for COVID symptoms today? By the way, this is a real project that has taken place. All right. We want to predict number of inches, that average number of inches that different locations on the East Coast are going to get in snow this year. And to better understand regression as a model, okay, so we can do regression just in the sense of we don't care if we're accurately capturing the hows, but we are going to get good predictions out, right? This black box gives me good predictions, right? That's the predictive way to use regression. But sometimes we hope to use the regression as a model to understand those hows and whys. So that would be the case with something like the sea ice. So we try to predict the effects of global temperature on sea ice thickness. Okay, so and if we use a bunch of different models to try to predict sea ice thickness given the temperature data for the year, does one of them do a lot better than the other? And if one of them does do a lot better than the other, one of these models we're investigating, maybe it actually captures something about how the interaction works, how it drives the changes in sea ice given temperature. And to lead you into the way the science on climate change actually works, it turns out this is a feedback loop, because when sea ice gets too thin, it changes the way the world's temperature works, because the melting of the sea ice changes the saltiness of the ocean, and it changes the reflectivity of the ice and whether it bounces the sun's rays back out into space or not. Okay, so there's a closed loop where temperatures affect sea ice thickness affects temperatures, back and forth. And we try to understand these complex iterations. Okay, so isn't that fun? So this is fundamentally a predictive exercise, but it can also be a causal exercise as well. Okay, it can be doing modeling. So I'm going to stop us here. And like I said, I'm going to do a bunch of shorter videos today so that we don't get too crazy with this multi-hour bonanza. So next up, we're going to focus on the inferential approach. All right, talk to you all soon.